minus alpha. And it is useful to write this n-dimensional integral by this one-dimensional integral. Okay, so this is just follow from 2D theorem. Okay, so here you integrate in t and from 0 to infinity of mu of the ball B as center at x and operator t, and then here you divide by t to the power n minus alpha. This is exactly the same power as this one. Okay. Another operator that I want to consider in this talk is the so-called fractional maximum operator, m alpha, where alpha is between 0 and n. So it defines very similarly to the maximal operator, but here you divide only to the power t to the power n minus alpha. In the case when alpha equal to 0, this is exactly the maximal function. And of course, for the definition, you see, and this property, you see that the fractional maximal function of order alpha is pointwise controlled by the fractional maximal function of order alpha. So pointwise, one is strictly less than the other, but if you look at them in an integral norm, then in fact, they are equivalent. So this is the classical result due to Muckenhoupt-Wheeden in the 70s. They show that for any q bigger than 0, and for any weight in the A infinity class, then the LQ norm of I alpha of the measure mu, for any measure mu, okay, with respect to this weight W, it is controlled by the LQ norm of the fractional maximal function of mu with respect to this weight, and the constant here depend on the A infinity constant of the weight, okay, and nothing else. I mean, some of course depend on Q and N as well, but the Q here could go to near. I mean, it could be as small as 2 watts. Okay. Okay, so let me recall that biasing W in the A infinity class. I mean that there exists constants C and mu bigger than 0, so that for any set E inside a ball B, the ratio of W E and WB, this is the integral of W over the set E, and this is the integral of W over the ball B. This ratio is controlled by the ratio, which is, I mean, and then you consider here with respect to the Lebesgue measure. So in some sense, the measure associated to W is controlled by the Lebesgue measure. Okay, so this is the definition of infinity weight, and there are many other equivalent definitions that I don't want to mention here. So that's the story in the 70s. So in some sense that if you look at integral norm, then the fractional maximal function and the fractional integrals are all equivalent. Okay, and because of that, if you use the pointwise power here, so if you raise both sides to the power q and then you multiply by the weight W, then you can control the derivative in the LQ norm with respect to the weight W by by the fractional maximal function of order 1 with respect to this norm. Okay, LQ norm for any weight in the infinity class. Well, you can view for some applications, you can view this. You can view this as like a pointwise bound. Why? Because imagine that if you are allowed to take W to be, say, the characteristic function of a ball, okay, then by Lebesgue differentiation theorem, then you can control pointwise derivative by the fractional maximal function. Okay, but of course you cannot do that because you have to work. I mean, this is true only for the A infinity class, but it's so what I'm trying to say that it's very close to to the pointwise bound, and for many applications this is enough. Okay, and so why? So of course this follows from the pointwise bound here, but why do I care about this integral bound? The reason is that this bound has the advantage that it could hold for more general linear uniformly elliptic operator with discontinuous coefficients, and whereas for the pointwise bound to hold, one needs at least say the linear continuous coefficient. Another reason is that for this bound, it is easier to handle up to the boundary of a bounded domain, okay? And finally, in many applications, at least in my application, this bound is enough for our purpose, okay? To certain nonlinear PD that I will tell you later. Okay, so the main goal of the talk today will be to obtain the Muckenhoupt-Wheeden type weighted bounds for gradient of solution to quasi-linear elliptic equation with measured data, okay, in the bounded domain omega. And we also discuss the Pointwise bound to the same equation. For this Pointwise bound, we will restrict to the range where p bigger than 3n minus 2 over 2n minus 1. So essentially, this number is like 3 halves. Okay. All right, and our goal is that to use, our ultimate goal is that to use those bound to apply to the problem of existence and solvability. Solvability and removability for the Riccati type equation. Okay, this is Hamilton-Jacobi type equation. Okay? And for this equation, we can deal with for all p and for all q bigger than equal to 1. We can also do with some with certain q less than 1 as well. I will tell you about that. And I want to make some remarks about the principal operator, where we can, in principle, we can replace the B Laplacian by with a more general operator of the form, say LP U in a divergent form, where the nonlinearity A here satisfies certain ellipticity and regularity condition. And for integral bounds, we need the coefficient to satisfy certain BMO condition in the X variable. But for the Pointwise bound, we need more. We need at least a Holder or a linear continuity condition in the X variable. All right. So let's see. And also because we are trying to deal with global bound, so we need some assumption on the boundary as well. So for us, C1 domain will be enough, and you can also generalize to like Reinberg flat domain, but I will not talk about it in this talk. So I will only focus on the B Laplace operator in the C1 domain, for example, for simplicity. So the first result is the Muckenhoupt-Wheeden type bound, the weighted type bound. This is your work with Quoc-Hung. So suppose that mu is a finite measure in the bounded domain omega, and p is bigger than 3n minus 2 over 2n minus 1. Q is a number bigger than 0. Then for any a infinity weight w, and for any renormalized solution u to this problem, you can control the derivative of u in LQ norm with respect to the weight w by the fractional maximal function of order 1 of mu here with respect to this weight. Okay. Now, there is restriction here for b bigger than 3n minus 2 over 2n minus 1. But in fact, we can also, in a recent work, we can extend it to the case where b up to, below this power 3 halves here. But in this case, we have to assume that q bigger than 2 minus p, and the weight have to be in the class A1 or a q over 2 minus p. Okay. And also in this case, we can only say that we can find a solution with this bound, but we cannot have this bound for all solutions. Unless we assume we know that the solution is unique. Okay. And I should mention that the use of the first order fractional maximal function to control the random solution to the B Laplace problem with measured data perhaps were first done in the work of Minchunne in 2010, and you can find that this kind of estimate, at least for the unweighted case and only local in the case when p bigger than 2. In that paper, you can see that there is some restriction on Q, say Q is less than or equal to P plus some small epsilon. The reason for that is that this will create the general general coefficient, okay? It's just measurable coefficient, and that's why you have to restrict Q to be below the energy exponent. And you cannot work with infinity ways there because of there is no assumption on the smoothness of the coefficient. And it's not, I think it's still not clear what kind of way you can put for general coefficient in this case, even when Q less than or equal to P here. All right. And the approach to this file, well, to prove this, you can use certain sort of kind of interpolation argument to get something like this. But because this is a nonlinear problem, so you cannot really directly interpolate to get the result. So what you need to do is that you need to connect the solution of your problem, okay, to a very good function, I mean, at any scale, So to do that, so you look at a solution W to the homogeneous problem in a scale, say R here, and W equal to U on the boundary of the ball, okay? Then you try to see how far, I mean, you measure the distance between the derivative of U and the derivative of W. It turns out that for the range P bigger than 3n minus 2 over 2n minus 1 and P less than or equal to 2 minus 1 over n, the difference here is controlled by the total mass, okay? But the total mass over that ball, I mean, the mu here is the one that's from the original problem, okay? Plus some nonlinear term here, okay? And you can see that if mu is 0, then of course this difference is 0. So it's when mu is small, then this is small. So it's measure the distance precisely. For P bigger than 2 minus n, this will obtain from the work of Mentionné-Duzat in 2011, and with the, you can choose even gamma 0 to be equal to 1 in that case, okay? And for P less than this power, okay, 3n minus 2 over 2n minus 1, this is still open, but in that case, you can take, I mean, you used to have to keep gamma 0 in this range on the right-hand side, on the left-hand side, but on the right-hand side, in that case, you can choose gamma 0 to be 2 minus P. If you assume that this is finite, okay, I mean, the relative U in L 2 minus P, then you can choose gamma 0 to be 2 minus P in that case, and that's enough for some estimates, okay, that I will tell you later. All right, and let me tell you the difficulty when B gets small. Well, the reason is that if you look at the fundamental solution to the Laplace equation, then the fundamental solution is given by this, and therefore the derivative is in the weak LQ space where Q is this n times P minus 1 over n minus 1. So from here you see that the derivative is in L1 even only if P is bigger than 2 minus 1 over n. So when P is less than or equal to 2 minus 1 over n, the derivative is not in L1, and this prevents us from using Sobolev inequality in the traditional argument. Because so in our situation, this power here is less than 2 minus 1 over n. But one of the important observations is that if you rate this fundamental solution to some power delta for small delta, and if you differentiate this, then it's in L1, and that you can do something, and eventually you can do it up to 3n minus 2 over 2n minus 1. All right? So now I'm switching gears now, okay? So I will move to the stronger estimate, Pointwise estimate, okay? So, I think to put everything in perspective, it's better to talk about estimate for the derivative for the function itself. Okay, and in the 90s, there is a groundbreaking result due to Kubelan and Mali, where they show that for Laplace equation with major data, I mean, you can control the solution two-sided pointwise by the so-called Wolff potential. Okay, and this is sharp, this is two-sided, okay, by the Wolff potential. So this is a nonlinear potential, and you see that there is a power 1 over p minus inside this one-dimensional integral. And of course, when p equal to 2, this becomes a truncated, Newtonian potential. But in general, when p not equal to 2, it's a nonlinear potential, and this is inside the one-dimensional integral. Okay, and well, about 15 years later, this estimate for the function has been, upgraded to derivative, and this is due to the work of Münchener and collaborators. So suppose that U is the solution to this Laplace equation with data measure data mu, and suppose that P is bigger than 2 minus 1 over n, then you can control the derivative of the solution pointwise by this linear potential with the power 1 over b minus 1. So this is n minus 1, okay? So the nonlinearity here is, the singularity here is n minus p. And this is n minus 1. So there's a difference here, okay? And the power of p, the power here is outside the one-dimensional integral, okay? It's outside. So basically, this is a linear potential raised to the power 1 over p minus 1, plus some tail here. This is reasonable because this is a local problem, okay? So, as I said, this is just a truncated first order linear risk potential of the measure mu. And historically, the nonlinear case with p equal to 2 was done from the work of Münchener, and the k p bigger than 2 were done in Münchener. But in this paper, for this paper, 1 over 1 minus b were inside the one-dimensional integral. Okay. So now let me discuss our results. So we obtain a very similar pointwise estimate in the case when p is now below 2 minus 1 over n. But we have the restriction on the lower bound. We require that p essentially bigger than 3/2, okay, in our work. And we have to use nonlinear potential here. So our estimate is very similar, but we have the power gamma 0 here. And gamma 0 is some power that below this radical exponent p minus 1 times n over n minus 1. Okay, the tail here is the norm of the derivative in L gamma 0 norm, and this is finite because the gamma 0 is allowed to be below this exponent. So, but we still have the gamma 0 inside our one-dimensional integral here, so it's a nonlinear potential. It's a Wolff type potential. Okay. Of course, you want gamma 0 to be big because the bigger gamma 0, the smaller your potential. But in our case, we cannot take it to be 1. Okay. Okay. Now, the proof of this, you can say that the bound like this is very close to the L infinity bound. Okay. So to bound something in L infinity norm, you can say interpolate between some LQ and then C alpha norm, for example. Okay. But you cannot really interpolate because as I said, this is a nonlinear problem. So you need something. You need something, some extra information to do that. And the first ingredient in the proof of that is that the comparison estimate that I mentioned earlier for small p. Okay. The second ingredient is that you need a very sharp quantitative estimate for the associated homogeneous problem. By that I mean that so if you look at the Laplace equation with right-hand side 0, okay, it is well known that this is classical result due to many people Di Benedetto, Tonsdorf, Evan, John Lewis, for example, and we know that the solution belongs to the class C, C1 alpha. And the classical, in the classical paper, you see that it is quantified by this way. Okay, so the derivative, the difference of the derivative at the point x and y is controlled by x minus y to the power alpha times some constant, and the constant is exactly the L1 norm of the derivative w. Okay, in a larger ball. But then somehow this estimate is not enough for our Pointwise estimate. And in the 2011 paper of Duza and Minjane, they have to redo this. Okay, they have to redo this C1 alpha estimate. They prove a very sharp quantitative way for the C1 alpha bound. Okay, so the left-hand side here is pretty much the same as the right-hand side here, if you understand the equivalent of Campanato space and Holder space. But the right-hand side here, you don't use, they don't have to use this just L1, they can use just the mean oscillation, okay? And I will tell you why this is good, okay? For us, but there is some problem here because for in our application, you cannot use it because this is still at the level of L1 norm. Okay, we have to go below L1 norm. So our result is as follows. So take the Q between 1 and P plus 1, and then look at this nonlinear vector field, U sub Q of C, C to the power of Q minus 2 times C here. Then we have a similar C1 alpha, C alpha estimate for this nonlinear vector field. Okay, so I want to say that this is by no means completely new, okay? The KQ equal to P for this scarp estimate can be found in the work of Dinning, Kaplinsky, Schwarzschild. For P bigger than 2, you can also find from the work of Duza, Minjane. And for us, but we cannot really yield those results directly. We have to reprove it and use it for us, we have to give with Q equal to 1 plus some gamma 0 for some small gamma 0 in our case. And our proofs, based on some of the idea in the paper, Asbi Fusco, Jakarta Modica. Okay. Now, let me tell you why this estimate is good for us. The reason is that, of course, you have some gain here. This is the way to say that this is C1 and C alpha. Right, C alpha. But the point is that the left-hand side and the right-hand side here have the same structure. Okay, they are symmetric, have the same structure. So it's allow you to iterate in your argument when you try to get the Pointwise bound. If you just want, if you remove this the average here, you cannot iterate your argument and you cannot really get what you want. Okay. So that for the Pointwise estimate, the local one. We also obtain a similar result up to the boundary. Okay, so if your domain is C1 is a C1 domain, then if U is a renormalized solution to this problem with 0 boundary condition, then you can control the derivative Pointwise up to the boundary with the same kind of potential, and then you integrate from 0 to 2 times to the diameter of your domain. But you lose something here. You have to put the distance to the boundary raised to the power, negative power for any small epsilon. Now, you shouldn't expect this to hold if you take epsilon to be equal to 0 because we work with a very bad domain, C1 domain. In the case, if the domain is C2, then we can take epsilon to be 0. This is the incoming work with Joel, with Banerjee and Quoc-Hung. Okay. Yeah, the right question to ask is that can we do it for C1 alpha domain where epsilon is equal to 0? It's not clear to us at this point, and this should be expected, but we don't know how to do it yet. Okay, so now finally let me mention about the application of Orbital estimate to the Riccati equation. So we consider this viscous, Hamilton-Jacobi tie equation with measured data. And it turns out that there is a capacity associated to this equation. Okay, of course, we know that the capacity associated to the B Laplacian is the B capacity. But if you add the actual nonlinear term here, there will be some interaction, and the capacity associated to this nonlinear operator is the S capacity, where S is Q over Q minus P plus 1. This is the Holder conjugate exponent of Q over B minus 1. Okay, assuming that Q is bigger than B minus 1. And why is that? So this follows from the following result. In the linear case, this result is due to Hansen, Mazur, and Verbitsky. And the same proof works also for the K when P, for the general P, okay? And this is known to Verbitsky. So suppose that mu is a finite measure and compactly supported in the domain, and suppose that Q is bigger than P minus 1, then there exists a constant C sub 1 bigger than 0, such that if this equation has a solution, then the measure mu has to be good, in the sense that for any compact set K, mu of K has to be less than a constant multiple of the capacity of the set K. Okay, so this is a necessary condition. So if you want to solve this problem, you have to work with, you cannot work with general mu, okay? You have to assume something on a measure mu. You have to assume some smallness assumption, and then you have to assume some regularity condition, and this is a necessary condition on the regularity of the measure mu, okay? And the question is, can we solve this equation under this regularity condition, okay? And this was an open problem posed by Verbitsky, and this problem was also raised in a 2013 paper of Maria Francois, Laurent, and Garcia Udupro, okay? And here we are able to address the problem pretty much in every case, okay? So we are able to show that, suppose that if your domain is C1, for example, and if P is between 1 and 2 minus 1 over n, and Q is bigger than or equal to 1, then suppose that there exists a C0 such that your measure mu satisfies this condition, okay, for some small C0, then you can solve the equation and you can obtain a solution to that problem, and the solution are based a similar inequality like this. Of course, this is also true for P bigger than 2 minus 1 over n. This was done earlier in 2014. And the case B equal to 2 is the classical result of Hansen, Mazur, and Verbitsky. The case when P, so here I work with all, so essentially this is for all P, but the case when P bigger than 1 and less than 3/2, and the case where B between 3/2 and 2 minus n are treated differently, okay? We don't treat them in the same way because there's some problem with when B gets small. So I will explain to you in a moment. So, well, we obtain a solution that satisfies this bound. So let me mention a little bit on the nature of the space of solution, okay? So the solutions that we obtain in this theorem are based that the derivative in this, in the space, which I call MQ1S. So the S here is the power Q over Q minus P plus 1. Sometimes I call this the Mazur's type space, but if you look at Mazur's book, this is called the Sobolev multiplier space. So let me explain that. So the space MQ1S here is the space of function f locally in LQ, such that this inequality holds for all phi in C infinity Rm. So this is the class of all function f in LQ locally, so that this inequality, I mean, this Poincaré-Sobolev inequality hold for all phi, okay? But the way here is f to the q. The way here f to the q. So this is the space of all weight f to the q, okay? All right. And a norm of a function f in this space is defined as the least possible constant c in this inequality. Now, by a capacitary strong tie inequality, this norm here is equivalent to this norm. Okay, so you take the sum over all compact set k of the integral of f, I mean LQ norm of f over the set k, and then you divide by the capacity of the set k, and then you take the sum over all for the compact set k. And then you see this is essentially this is what is formulated here. Okay, so so here you just replace f by raq here. So how do you handle the norm of this space? Okay, because you take the sum over the compact set. If you restrict the set k to be the ball, then what you get is the Morey space, which is easier, much easier to handle. But here you have to take the sum all over the compact set k. So it's not that simple to handle. Okay. Now, one way to handle this norm is that you have the following equivalent formulation. Okay. For any q bigger than 1, this norm is equivalent to this supremum. You take the sum over all weight w, I mean of this integral here for all weight w, where the weight is taken all over function w, and w in the class A1C. I will explain to you in a moment what it means to be A1C. And the A1C of w is less than or equal to 1. And the w is in the A1 local class with certain bound, and the constant c here is independent. I mean, it's just depend on n and s here. Maybe I should say q here. Okay. Now, it is easy to see that this norm here, because this is for all compact set, so it's easy to show that this norm is equivalent to this when you take the w to be overweight without this A1 local condition. So this norm is equivalent to the supremum like this, where you take the w to be running over the weight without the A1 condition. Okay, and the weight of course has to be in this A1C. By saying A1C, I mean this norm here. Okay, I mean this is very similar to Lebesgue space. So you look at the set where you look at the super levels, upper level set of W, and then you calculate the capacity of that set, and then you integrate along the T here, and then what you get is what you call A1C. Okay. So the point of this theorem is that you can restrict the sum over only the A1 local function W. You don't have to take over weight. You can just take weight that are good, say A1 local weight. Okay. And of course, this is very closely related to the work of Verbitsky in the 80s. So what we do here is pretty much a reformulation, functional analytic reformulation of his work. And I want to mention something about this space, okay? It's very similar to Morey space in the sense that it is also a dual space, okay? And you can find many characterization of the pre-dual to this space from our work, from my work with Oy, and also from the work of Calder and Verbitsky. I don't want to go into details here. And you can also treat a similar situation where you replace the 1 here by the alpha, the rational alpha. But this is very subtle to deal with this case, because in the case when you deal with alpha equal to 1 here, this functional here is a sublinear functional. Okay, so it's a norm. But for alpha, for non-integer alpha, it's not clear if it is a norm. Okay, but you can show that it's normable. Okay, and from there you can apply Hahn-Banach theorem and so on, and you can get what you want. But it requires a lot of work. Okay. Okay, so that's I want to make I want to tell you a little bit about the nature of the space of the solution. Now, I want to mention some other cases and unsolved problem for this Riccati equation. So in my work here, in our work here, we treat the case when Q bigger than or equal to 1 because we need some convexity in our argument, okay? Now, if you can also do it for Q less than 1 and P bigger than 3/2 here, okay? This is our recent work with Quoc-Hung. But in this case, we have to work with compactly supported measure. And in this case, we have to use the full force of the Pointwise gradient estimate. We cannot use just integral estimate to obtain our existing result. Okay, we have to use the full force of Pointwise estimate. Okay, so that means that we have to assume more on the boundary. We have to assume more on the coefficient and things like that. Okay, and you can also talk about the case when Q is between 1 and this Riccati exponent where P is less than this power, but this is still not clear to us yet. The case when Q is less than this subcritical exponent was done by many people. I want to mention here just a few words. You know, Renon, Mura, Foresta, Better, Mercado, Mura, Bosio. I mean, there are many others work as well. Okay. Okay, so there are also other unsolved problems, and there are also other cases that I want to mention next. First, this is the situation where we talk about distributional data. Okay, so if you look at this existing result, you see that if your measure mu is non-negative, so this is will be a sharp result because this is necessary and sufficient condition. But if your mu is side changing, this condition turns out to be no longer a sharp condition. Okay, it's no longer a sharp condition because you take the absolute value of your measure. That means you destroy some cancellation, you know, inside your data already. So how do you deal with that? So we need to find a very reasonable necessary condition to deal with that. And the necessary condition is that suppose that your Q is bigger than P minus 1, and suppose that your mu now is a general distribution in your boundary domain. Okay? Then if the Riccati tie equation admits a solution U such that the solution is in this Mazur tie space or in this Solet multiplier tie space, then we can show that the datum mu here cannot be arbitrary. It has to be in divergent form. Okay, so if there is a solution, and if the solution is in this natural space, this is a very natural space, then the datum mu here cannot be arbitrary. It has to be in the divergent form. And the vector field associated to this measure mu here also obey a very similar estimate, meaning that it is also in the Mazur tie space, I mean the Solet multiplier space. And that's the necessary condition. Okay, so if you want to work with general data, I mean any distributional data, then you have to work with divergent form data, and the vector field have to satisfy this condition. So the question is, can you show existence under this condition? And we are able to do this in the case when Q bigger than or equal to P. The case when Q less than P is still open. Okay, we don't know how to do it. So let me tell you this. So for Q bigger than or equal to P, we get existent result under this condition. I mean, where mu is in divergence of F, divergence of F, where F is in this space and C is small here. And this follow from our recent work with Quoc-Hung, and some other result in Moray space. You can also find in my work with Mangesha. For the particular K equal to Q, this is actually a very interesting case because it's a connection to the Schrödinger tie equation. Okay, using some exponential transformation. So and this was done. I mean, there's some related work to this, and this was done in. You can find it in the paper of Federer, Mura. I mean, many work. Adimathi and myself, J, Mazda, and Babitsky as well. Okay, but the general case when Q bigger than or equal to P can be found in this recent paper. Okay, so let me tell you an example where this condition, okay, is better than this condition. Okay, the example is that you have to work with, I mean, you have to take, of course, the measure and the data has to be non-negative, I mean, side changing. Okay, so you look at this side changing data, okay, act to some power here. You choose epsilon and s so that this is a locally integrable function. Okay, so epsilon plus s is strictly less than n. Then you see that if you take the absolute value of f, then it's no longer satisfy that capacitory condition. It failed to satisfy that capacitory condition because this actual power, actual epsilon here. Now, but if you rewrite f, okay, you rewrite f at a divergent in a divergent form, so you can easily find an f, so that f can be written as the divergence of some vector field f plus a good function, and actually the vector field f is explicit. It is written like this. Then you can apply this condition. I mean, this condition will be satisfied, okay? And you can apply this result and get the existing result, okay? So there is advantage when you formulate this, and of course, this is more general than the situation with measured data, okay? So the study of this Riccati equation with distributional data has motivated us to study this problem, okay, with divergent data, okay? I mean, data in divergent form, okay? So it's more general than measured data, but it's very difficult to control solution for this kind of equation. Because I mean, there is some conjecture associated to this. I will tell you. So what you can do is that you can bound this, you can bound a random solution to this innovative norm here, but you have to work with Q bigger than P, okay? And the way is a Q over P. For the for the unweighted for the K when the weight is 1, I mean this follow. I mean this was first done in the work of Iwanya. You can also find it in the work of Barao, Kafan Lee, and many other work like Kinunan and Zhu on abiotic domain, Bayun and Wang, and many others work. And for the linear case, this is a classical equation, and it was done, for example, in one of the papers of Yifajo and many others. Okay, but here I'm talking only the K1 for general beta plot operator. Well, the case, it turns out that you can also do something with the K Q equal to P, and you have, in that case, you have to assume that the weight to be in A1 class. Okay, and this is done in my work with Adimathi. And even for, of course, this is very strongly related to the work of Iwan Yak, Spodan, and John Lewis about higher integrability of Villa-Plata equation with zero right hand side. Now, the K when Q less than P is still open, okay, and this is known as a conjecture of Iwan in the 80s. So finally, I want to mention about the application of that existing result. Well, you can show that with that existing result, you have the you can characterize removable sets. Okay, so if a set E, if a compact set E inside domain omega is removable, is a removable set for this equation, then it must hold that the capacity. I mean, this is the capacity of the set has to be 0. Okay, and this is true for all, basically for all P when Q is bigger than or equal to 1. And you can also say something about the K when Q less than 1, but you have to ask that P bigger than P halves, okay? And so the necessary condition for a removable set is that the capacity is 0. So now, and actually this is sharp, you can also go the other way around, okay? So at least in the class of B super harmonic function, okay? So precisely, we have the following results that if E is a compact set in the domain omega with zero capacity, then any solution outside the set E, okay? Here, you just need the derivative to be LQ locally away from the set E. Then you can extend it to a solution inside the whole domain omega. In the case when Q bigger than P, you need U to be, you need to assume that U to be super harmonic inside the whole domain omega. But when Q is less than or equal to P, then whenever this capacity is zero, then the big capacity is also zero, and then you have this automatically. So you don't really need this in the case when Q is less than or equal to P. Okay. So I guess that's all I have to tell you. Thank you for your attention, and happy birthday to the veterans.